Okay, so basically the next thing that we have here is basically something called the converse of a statement, which is basically extensively used in, at least as far as I know, in geometry. The converse of a statement. Okay, so what that is that basically in order for the concept of the converse of a statement to be meaningful, you basically need to have a compound statement. And what a compound statement is, basically you can have something called a simple statement. You can have something called a simple statement and something else called a compound statement. A simple statement is basically one simple statement, and just as the name implies, it's just a simple statement. For example, it is raining today, something like that. So that's a simple statement. Now, if you put together basically two or more simple statements in, and basically it's possible to put simple statements together in many different ways. Now, one of the ways that you can put simple statements together is using if then. Is using if and then. So if you use if then and then put a couple of simple statements together, you'll get this compound statement. For example, let's say that you have as P, you have it is raining. It is raining. Okay? And as another statement here, you can say it is difficult to go on a bicycle. It is difficult to go on a bicycle. Okay? So I have these two statements over here. And each of these statements, if you basically consider them individually, they are basically simple statements. This is a simple statement. This is a simple statement, and this is also a simple statement. Okay, so now of course that's basically only one way that you can put these simple statements together and make a compound statement, and one of the ways that you can do it is using if and then. Otherwise, there are other ways as well. So now if I use if then in order to put these two statements together, so basically what I will get is that if, for example, if P, what I'll get is if P, if statement P, then statement Q. Okay? So, and what that means is that I can say if it is raining, comma, then it is difficult. Then it is difficult to go on a bicycle. Okay? So that's, and now basically what you have here, this statement over here, is called a compound statement, because it's a combination of two simple statements using if and then. Okay, so now what we want to do, we want to basically create the converse of this compound statement. The converse of this compound statement, statement is, if you have basically if P then Q, the converse of that would be if Q then P. Okay, so and basically when you have if P then Q, you can of course write it as P implies Q, P implies Q, and denoted by P implies Q. Okay, so that's basically how you can write this. And then if Q then P, then you can instead of if Q then P, you can also say P Q implies P, and then also denoted by Q implies P. Okay. Now let's take an example over here. There is a good example over here. It says that if the water tank is black, if the water tank is black, then it contains portable water. Then it contains portable water. And if it doesn't make any sense to you, it's just because in India it's just like that. In India, portable water is in black containers. So that's how it is in India. Anyway, now over here, this statement is of the form P implies Q. Okay, now P basically over here is called your hypothesis. P is basically called your hypothesis, and Q is basically called your conclusion. So that's basically your hypothesis, and that's basically your conclusion. So that means that your hypothesis is that the water tank is black, and your conclusion is the tank contains portable water. Okay. So now if you interchange the hypothesis and conclusion, what you will get is basically if you interchange the hypothesis and conclusion, what you will get is Q implies P, and that would be the converse of the converse of this statement over here. And what this means is that basically what this statement would be in language form is that if the water tank contains portable water, if the water tank contains portable water, then it must be black. Okay, and these are two completely different things. I mean, the meaning is completely different. Here, your hypothesis, or basically the condition, is that the water tank has to be black, and then if it is black, then it contains portable water. But in the second case, the hypothesis, or basically the condition, is that if the water tank contains portable water, if it already contains portable water, then it must be black. And so that's basically that. And this concept of converse is extensively used in geometry. And basically in geometry, it's like, for example, you say one thing. Sometimes, for example, you talk about the theorem that, for example, I don't remember. For example, the Midpoint Theorem, for example. You say that if, for example, in a triangle, let's say that you have a triangle over here. If I probably don't remember this properly. If you say that, for example, there is some theorem related to triangles, and that is, if you pick the midpoint of this side AB, okay, so that means that this length is equal to this length, meaning that this side, this point, for example, D is basically the midpoint of A and B, okay? And if you draw a line parallel to BC through D, meaning that if you draw a line like this, that line is going to cut AC at the midpoint of AC. That means that then basically these two distances are going to be the same. Okay? So now in this situation, you need to be careful about what you're assuming and what you are given, meaning that what you're assuming, basically what your hypothesis is, and then what the conclusion is. So over here, the way that I set this, was that first of all, I know that AD is equal to BD. AD is equal to BD, meaning that D is the midpoint of AB. And also, let's say that this is E, for example. And also DE is parallel to BC. Okay? So this is my hypothesis. This is my hypothesis. And then as a conclusion, what I have is basically AE is equal to EC. AE is equal to EC. So you can take this as P, and you can take this as Q. Okay, so then this is basically not very really important, but this is called the Midpoint Theorem. The Midpoint Theorem. Okay, so now sometimes in geometry you have a situation like this where, for example, you have these two conditions, and then you prove that, for example, E is the midpoint of AC, for example. Now if you have basically the converse of this situation, for example, the converse of this situation would be if this is the midpoint of, if E is the midpoint of AC and also D is the midpoint of AB, then DE is going to be parallel to BC. Okay, so that would be the converse of this statement. So sometimes basically this is true, and then you can somehow manage to prove that basically the converse is also true, but sometimes only basically sometimes it's only a one-way street, meaning that sometimes the only thing that you can prove is that, for example, if these conditions are fulfilled, then basically you will have this sort of conclusion, and you cannot, and then of course you cannot go from here to here. You cannot go. You can go only from here to here. Okay, so that's basically the meaning of this whole business of converse of a statement. So now we have a couple of examples here. We will go through each of them one by one. They are simple, and we will see what we'll get over here. Okay, so the first example that we have here is basically if Jamila is riding a bicycle. If Jamila is riding a bicycle, then 17th August falls on a Sunday. Then 17th August falls on a Sunday. Okay, so basically this statement, as you can see, is in the form P implies Q. P implies Q. So all you need to do is basically identify P. All you need to do is basically identify P and Q, and then basically write your statement in the form, write it as Q implies P. Okay, so now here basically your P basically is this statement over here, and your Q is this statement over here. So now Q implies P would be so basically this becomes your if clause, this becomes your then clause. So if 17th August falls on a Sunday, then Jamila is riding a bicycle. Jamila is riding a bicycle. Okay, so that's the first one. Now, the second one, these are all basically the same thing, so we don't really have to spend much time here, and there would really be no confusion here. So and of course I need to emphasize the fact that basically here we actually do not care about the truth of any of these statements. all we are concerned about is actually just writing the converse of these statements and the process, basically, that the process of doing that. Otherwise, it doesn't really matter if this statement is true or not. I mean, in this case, not that it doesn't matter in all cases, but in this case, it doesn't matter really. And then we have some other examples here. And then the next thing that we have, remember, the next thing that we have is proof by contradiction. We don't really have to stay here any longer. These are simple and you simply understand them. So then the next thing that we have is proof by contradiction. So proof by contradiction. Okay, so what that means, so basically by now we have proved basically proved our statements in two ways. First of all, there was the case of the counter example, and second of all, we had the basically we had something which was, I think it was called logical deduction. Logical deduction, if I'm not wrong. Basically, by logical deduction, I mean the case that we had the triangle, and we wanted to basically show that the sum of the internal angles of that triangle was 180 degrees. Okay, and the counter example was the example of the two, basically, the product of two odd numbers that was supposed to be even numbers, and so on and so forth, and we found a counter example to show that this statement was false. Now, the proof by contradiction actually works in a slightly different way. Meaning that in proof by contradiction, what we do is that intentionally we create some sort of contradiction in the process of proving, and then from that contradiction we conclude that basically we come to the conclusion that we want to come to. Okay, so now if you didn't understand what I said, let me give you an example to make it clear. So it says that basically a contradiction is basically, in mathematics, a contradiction occurs when we get a statement P such that P is true and not P and the negation of P is also true. So we said that basically if we had a statement P, the negation of that statement was not P. And basically we also said that if we wanted to check whether we had done the negation right, the condition for that was that if P is true, then not P has to be false, and vice versa. Meaning meaning that if P is false, then not P has to be true, because P is the negation of not P, and not P is the negation of P. If one of them is true, the other one has to be false, and so on and so forth, and vice versa. Now a contradiction happens. A contradiction happens if basically if P and not P are both true, or both false, because that simply cannot happen, meaning that if P is true, then not P of course has to be false, and if P is false, then not P has to be true, because P again is the negation of not P, and not P is the negation of P. So they cannot simultaneously have the same condition, meaning that they cannot simultaneously, both of them cannot be either true or false, meaning that, and if that happens, meaning that if both P and not P, if both of them are true or if both of them are false simultaneously, that means that there has to be some sort of contradiction. For example, let's say that for example, let's say that P is some statement that I make, that I say my bicycle is red, and not P would simply be my bicycle is not red. So now, even by the meaning of these statements, you can understand that if my bicycle is red, if this statement is true, then of course this statement has to be false, because my bicycle cannot be red and not red at the same time. Or basically, if this is false, if it is false that my bicycle is red, if this is false, this has to be false, this has to be and I'm sorry, if this one is false and this one is also false at the same time, then that also cannot, basically simply cannot exist. Meaning that at any time, if P is true, not P has to be false, or if P is false, not P has to be true, because they are the negation of one another. Now suppose that it just so happens that at the same time my bicycle is red and also my bicycle is not red. Both of them are true. So then there has to be some sort of contradiction in my logic, because again, at the same time, my bicycle cannot be red and not red at the same time. And we use the fact that this contradiction cannot exist. The fact that this contradiction cannot exist, we use it in order to prove some of the results that we have. So for example, let's see. How does it prove? Given the following: all women are mortal, A is a woman, prove that A is mortal. So I guess I don't have to give you an example here. So we can simply now go to we have a couple of examples that will explain this proof by contradiction pretty well, so I don't have to give you a headache over these examples, and the example that we have in the main examples in the book, it's about real numbers. We will go through that example, and you will see actually a good example over there. But if you want to see the example right here, so let me actually go over there and show you the example. So it is somewhere over here. Somewhere over here. And I guess it was around this gamma, and I suppose okay, so for example, let's say that okay, so for example, let's say that you want to prove that square root of 2 is irrational. Okay, you want to prove this. So how do you do it using proof by contradiction? It's actually very interesting. So for the proof, you say that we assume that to the contrary, square root of 2 is not irrational but rational. Okay, so we want to assume that to the contrary, that square root of 2 is actually rational. Okay, so if basically you know the definition of rational numbers, and you know that the rational number is is a number that can be expressed by the ratio of two integers p and q, for example, where basically p and q are integers, belong to the set of integers, and q is not equal to 0, because you're not supposed to divide by 0. So then in that case, p by q, whatever that is, if you call it 8, and then a is basically a rational number. Okay, that is a rational number. Otherwise, if it's not possible, let's say that there is some number b, which is, and in the case of this number, it's not possible to express it in this form, then this number is simply called an irrational number. Okay, so that's basically the definition of rational and irrational numbers. So now we actually use this definition over here in this proof in order to prove that square root of 2 is irrational, and we have actually assumed that to the contrary, meaning contrary to the fact that we wanted to prove that square root of 2 is irrational, we have assumed to the contrary that square root of 2 is actually rational. Okay, so if that's the case, so we can actually find integers. We can find integers r and s, s not equal to 0, as we mentioned before, such that square root of 2 is equal to r divided by s. right? Such that the square root of 2 is equal to r divided by s. That's based on the definition of rational numbers. Now this is the part that these are the parts, for example, that are important. You see, for example, if you basically if you express some number, for example, let's say 8. If you express 8 as a ratio of two numbers, 8, you know that it's an integer, it's a natural number, it's a whole number, and of course it's a rational number as well, because you can actually express it as a ratio of two integers. For example, you can write 8 as 8 divided by 1. You can write it as 16 divided by 2. You can write it as 32 divided by 4, and so on and so forth. Okay, so there are actually an innumerable number of rational numbers that would express actually the number 8. Okay, but there is only one case among basically all of these numbers that you would get all the way up to infinity. There is only one case in which basically your numerator and denominator have no common factors, meaning that 8 and 1 have no common factors except 1. And for the same reason, these two numbers are called coprimes. Meaning that they have no common factors except for 1. So now I want this fraction to be the two numbers in the numerator and denominator to be actually coprimes, because first of all, it makes things a lot simpler, but there has to be some other reason that I might tell you in the process, and right now I really don't know. Okay, but okay, so anyway, we have basically R and S. Now here we say suppose that R and S have a common factor other than 1. R and S have a common factor other than 1, meaning that they are not coprime. So then we divide by the common factor, divide basically both the numerator and denominator by the common factor, to get square root of 2 is equal to a to b, where a and b are coprime. Where A and B are coprime. I suppose now you understand these senses here, meaning that, for example, the number 8 is basically, if you express it as 16 divided by 2, now in 16 divided by 2, 16, you can write it as, for example, you can write it as 8 times 2, and 2 you can write it as 2 times 1. Now these two numbers, as you can see, they have this common factor except for 1, and so they are not coprime. So now you take both of these numbers and divide by the common factor. So 16 divided by 2 is equal to 8, and 2 divided by 2 is equal to 1. So then this fraction becomes 8 divided by 1. Now this is actually what you have here. 8 divided by 1 is basically this a to b over here. Okay, so that's basically what is meant by that. So then you get basically, you take both of your numbers and divide by the common factor, and you get square root of 2 is equal to a divided by b, where a and b are basically now co-prime, so we have no problem there anymore. So now if you rearrange this equation over here, rearranging the equation, you will get basically, if you have basically square root of 2 is equal to a divided by b. So if you give this a denominator one and you simply cross multiply, you will get a is equal to square root of 2 times b. Square root of 2 times b, or okay, so a is equal to square root of 2 times b. And if you square on both sides, squaring on both sides, what you will get is a squared is equal to 2b squared. So that's a squared, square root of 2 squared is equal to 2, and b squared, b squared is simply b squared. So what that means is that now the meaning of this, what we have written over here is that a squared is actually divisible by 2, because a squared has been written as a product of 2 and some other number. So that means that a squared is divisible by 2. So that means a squared is divisible by 2. Okay. Now, in order to familiarize you more with the language of this book, and also with the language of mathematics, if you say a squared is divisible by 2, another way of saying the same thing is that you can say 2 divides a squared. So when you say 2 divides a squared, that means the same thing as a squared is divisible by 2. Okay? So now we have a theorem that we will talk about later, but for now I'm just going to use the theorem without proving it or anything. And the theorem is basically if you have some number, for example a squared, if it is divisible by some number b, what that means is that a is also divisible by b, and that actually makes logical sense. For example, let's say that for example 9 is divisible by, let's say that 9 is divisible by 3. Okay, and of course you know that 9 is equal to 3 squared. Okay, so if 9 is divisible by 3, then what that means is that the square root of 9, which is equal to 3, is also divisible by 3, meaning that if you take 3 and divide it by 3, it's going to give you 1, remainder 0. So that's basically this whole theorem. Now I'm going to use this theorem in order to conclude that, that means a squared is divisible by 2, and so a is also divisible by 2. Okay, a is also divisible by 2. So so what that means, using the theorem for later, basically we'll talk about that later. Okay, so what that means is that if a is divisible by 2, so we can write basically a as 2 times c, because it's divisible by 2. It can be written as the product of, for example, some integer and 2 for some integer c. For some integer c. Okay, and then if you substitute a for now, if I call this equation number 1, and if you substitute in number 1, what you will get, a is equal to 2c. So over here I have a squared is equal to 2b squared, and if a is equal to 2c, so 2c whole squared is equal to 2b squared, and that is 4c squared is equal to 2b squared, and that would be a 2, that would be a 1, so that means that 2c squared is equal to b squared. And what that means is that, and what this means is that b squared is b squared. So what this means is that since b squared can be written as the product of 2 and some other number, that means that b squared is divisible by 2. Okay, and so b is also divisible by 2 based on the same theorem that we talked about. So if b squared is divisible by 2, so b is also divisible by 2. So now here we said that a is divisible by 2, and also b is also divisible by 2. Okay, so what that means is that a is divisible by 2, and b is also divisible by 2. Okay, so but the problem here is that here we said that then we divide by the common factors to get the square root of 2 is equal to a by b, where a and b are coprime. So we said that, and we said that a and b were coprime. Okay, so when we say that a and b are coprime, that means that they cannot have any common factors other than 1. But now here we can see that they have a common factor which is equal to 2, because a is divisible by 2, meaning that you can write a as the product of 2 and some other number. So 2 is a factor of a, and also b is divisible by 2, meaning that 2 is also a factor of b. That means that 2 is a common factor of a and b. But then over there we said that basically a and b were supposed to be co-prime. So this is a contradiction, right? So therefore a and b have at least 2 as a common factor. A and b have at least 2 as a common factor. Okay? But this is a contradiction, but this basically contradicts the fact that a and b have no common factors other than 1. That basically a and b are co-prime, meaning that have no other factors other than 1. Okay? And this contradiction has arisen because of our incorrect assumption, that square root of 2 is rational. Okay? So we conclude that square root of 2 is irrational. And that's basically what we wanted to prove, that square root of 2 is irrational. So that's basically one example of, that is basically one example of proof by contradiction. Okay? So what I did here was that, let me walk you through this, let me walk you through the steps. So we wanted to prove that square root of 2 is irrational. Okay? So first what we did, we assumed to the contrary that square root of 2 was rational. We wanted to prove that it was irrational. So we assumed that it was a rational number. And then, and so if basically a number is a rational number, based on the definition of rational numbers, you will be able to find 2 integers and express that number in terms of those 2 as the ratio of those 2 integers r and s. Now here we assume that, for example, those 2 integers r and s could have a common factor other than 1, and this is a step we have done, because if we hadn't done this, otherwise we wouldn't have been able to basically use a and b in the end in order to get to the contradiction. Okay? So now we suppose that it's a safe assumption to make, and it's well possible that r and s have a common factor other than 1. So then we divide by the common factor to get basically, and then the numerator and denominator will simplify. From r and s you will get simply a and b. But now here basically the benefit of doing this step is that now we have made sure that A and B have no common factors other than 1, meaning that they are co-prime. So now if you rearrange this equation, and you will be able to write this as A is equal to square root of 2 times B, and if you square both sides of this equation, you get A squared is equal to 2B squared. So now what that means is that basically 2 is a factor of A squared. So what that means is that by this theorem that we will talk about later, 2 is also a factor of A. So that means that A is basically divisible by 2, right? So that's about A. So that's about A. So we can write A as 2 times C for some integer C, meaning that 2 is a factor of A. And then if you substitute A in this equation over here, you'll get A squared is equal to 2B squared, and A was equal to 2C, so 2C squared to 2B squared, and so on and so forth. So B squared is equal to 2C squared. So that means that now B squared is also divisible by 2, meaning that B is also divisible by 2. So 2 is a factor of B as well. So now we have established that 2 is a factor of A and also a factor of B. Okay? 2 is a factor of A and also a factor of B. So A is divisible by 2 and also B is divisible by 2. But we said that A and B were co-prime, which is not possible. If they are co-prime, they're not supposed to have any common factors other than 1. So so what these actually mean is that A and B have at least 2 as a common factor other than 1. And this contradicts the fact that A and B are co-prime. This actually contradicts the fact that A and B are co-prime, and this contradiction has arisen because of our false assumption or incorrect assumption that square root of 2 is rational. The assumption that we made that square root of 2 was rational was actually incorrect. Otherwise, this contradiction would not have arisen. And so based on this, we can safely conclude that square root of 2 is irrational. Okay? Now, of course, there is some so basically what we are saying is that basically this contradiction has arisen. Okay, that makes sense, of course. So that's basically how you prove something by contradiction. So you create that contradiction in the beginning as an assumption, and then in the end you will conclude that basically you will see some sort of contradiction coming in, and then of course you can see that contradiction has arisen because of your false assumption. So then you can conclude that your assumption was false. That means that the negation of that assumption is true, and the negation of that assumption is basically what you wanted to prove, and that's basically how you prove by contradiction. It's actually an interesting way of proving things, which is a little bit, you're just moving around yourself in circles. But I suppose, since it works, so why not? And well, of course, it's an elegant way of using logic in order to get to what you want, although it might actually be a little bit complicated. but who knows, maybe if we didn't have this basically this tool over here, which is proof by contradiction, maybe we would not be able to actually prove this thing. So that's basically how this actually works. Okay, so that's basically all that we have over here about mathematical logic and proofs in mathematics. So we are at the end of these few videos. In the next video we will talk about these couple of theorems about real numbers, rational numbers, and irrational numbers. So I'll see you in the next video. Thank you.